pleased to introduce Dr. Barry Mather, who is with the National Renewable Energy Lab. He's a power systems engineer there. Until 2015, he led a project addressing technical impact of integrating high levels of solar in Southern California Edison service territory. He's also authored the High Penetration PV Grid Integration Handbook for Distribution Engineers. He received his PhD in electrical engineering from the University of Colorado in Boulder. And once again, pleased to welcome back Dr. Kevin Schneider, a principal research engineer at Pacific Northwest National Lab. Take it away.
Okay, perfect. Yeah, thank you all for joining here remotely. Do apologize and missed the opportunity to go down to Jackson. I heard Bully's restaurant was, is very famous, and that's where I was hoping to, try some good soul food, but I'll have to wait for another day. So yeah, we'll go through the presentation here. I just was talking with Kevin. Probably I will probably lead most of the presentation, and Kevin will jump in here and there just because of the different format than we're used to giving it here. But let's start really with what we mean by distribution system automation and control. You heard a lot about, I think this is exactly the right place for this sort of presentation to be within the agenda. For instance, this morning from Paul, you heard a lot about the planning, right? And that the idea is you got to have the strategic plan and that sort of stuff. Distribution automation is specifically one of those technologies that he mentioned, where, and we really are going to talk about the technology side for the next 45 minutes. It's one of those areas where you effectively get a lot of potential stacked benefit, and you'll actually see how exactly that works. That distribution automation can be seen, distribution automation and control in general can be seen as one of those things that actually does many things, right? It's not necessarily put in for one specific use, but actually for multiple uses. And again, following Emma's presentation, sensors, actual actuators, that sort of stuff is really all what we're talking about. So if we look kind of at this formal definition of distribution automation, it's really it uses sensors and switches, or really we could say, grid level equipment with advanced control and communication technologies to automate feeder switching, voltage and equipment health monitoring, outage and outage monitoring, voltage and reactive power management. So it's a pretty broad definition. I would say it's probably even a little bit broader than that, but that's a pretty good definition, I think, that we found. What we're trying to do with distribution automation and control is really from a utility and a customer perspective. We're trying to, one of the classic cases is, mitigate outages, right? Either avoid them altogether or make them shorter, right? So much faster restoration of customer service, improved resilience during extreme weather or other events. Just improved resilience in general is a very important one. More optimal equipment maintenance and usage. So Kevin was talking about transformer utilization earlier. That sort of stuff, really trying to utilize all assets on the distribution system more effectively, more efficient of actual utility, time of crew time, for instance, is a big one that is oftentimes used with distribution automation and control. And the other thing that this can really drive is it's effectively a big tool that allows more visibility and control to actually enable, say, the integration of distributed energy resources, things like distributed PV. So as Lisa mentioned, I'm from the National Renewable Energy Lab. Obviously, our interest is in pushing, completing research effectively to enable the integration of higher levels of distributed energy in the form of renewables, which is obviously the biggest driver for distributed energy resource growth in the United States right now. But the same can also be true said for loads, right? So electric vehicle charging is obviously a big deal in many different locations, and generally all these different grid modernization efforts. Let's go to the next slide, slide 3, please. Perfect. So I just want to give a few examples of kind of, say, some simple or historic examples of distribution automation. They really can range from very simple systems to very complex systems. So just trying to start with, I'll give an example here of what's called a auto loop recloser or loop recloser automation. It's a good example of something that kind of serves a single function, right? It has it has one specific use that it is quite good at. The equipment is usually controlled kind of locally, right? It's not all the control of that sort of equipment and how it works, the automation, if you will, doesn't necessarily require lots and lots of communication all the way back to, say, a central management system at the utility. It can be basically done locally, and the relative number of kind of potential operating scenarios is somewhat limited, right? Basically, they're simple, right? The number of states that the system can be in is not some massive number, right? And I'll follow this up with a complex example of advanced distribution management systems, which I'm sure people are probably familiar with that term. This is really where you get into that stacked benefit, right? You're serving many functions. And we'll actually talk later in this presentation about, say, advanced metering and how it serves, multiple different functions, and those value streams from all those functions stack up to give the total value that, of course, the customers and the utility are looking for. And the equipment, tends to be controlled across a wide area, lots of different types of equipment, that sort of stuff. And at least when done correctly, those systems are seamlessly integrated. So let's first talk about, a simple example, this auto loop recloser distribution automation. Let's go to the next slide, please. So in this case, the goal is pretty simple. It's to decrease outage duration and impact. These are actually fairly widely used, especially in certain utilities. I wouldn't be surprised at all if down in the Southeast, this is actually pretty common, typical design almost of how, of a distribution automation application that it might be used quite often. But the idea is that you have two adjacent feeders. In normal configuration, they are operated, normally, just in a radial normal fashion. But really the way loop recloser automation works is that you have a tie breaker, that's that green breaker there in the figure, and it is usually open, right? So basically at the point where two feeders kind of meet, they operate normally radially, but that switch is usually open during normal operation. The idea is that if there is a fault, say a tree limb touches one of the lines, overhead line, for instance, within one of the sections, say section 2A there at the lower left, the idea is that the system automatically basically detects that fault, clears that fault, right? Actually responds to that fault by opening, say, a circuit breaker. But then it actually restores the customers that it can via a different path. So for instance, if that fault happens in section 2A, the circuit breaker there in the lower left would operate, as would the red box to the right. And then what eventually would happen in this equipment is automated, so it's actually communicating amongst itself and figuring out, okay, how do I bring the most number of customers back on? The idea would be that after a short outage, the tiebreaker would close and would effectively bring that section 2B and 2C back online, right, via the other feeder. So it's really an automatic reconfiguration type scheme meant to, again, reduce customer outage and that sort of stuff. The idea would be that at the end of the day, you only have section 2A that's actually outaged, because that's where the actual fault happened. And of course, the truck crew would run out there, clear that fault, fix whatever's wrong, that sort of stuff, and then eventually the system would be back up and running. But during that actual fixing period of time, at least 2/3 of the customers on that lower feeder would not have an outage. The system operates autonomously. It has a single function, right? It's really meant to decrease outage, impact, and duration, keep most customers up online. And this equipment talks, communicates with itself. And to be honest, most of these are implemented kind of using a proprietary, if you will, system that you buy from a vendor, and that's what its single function is. Let's go to the next slide, please. This can get very complicated very quickly, right? Because that example I just gave, was a very simple feeder. This is what things look like more in reality. This obviously is not a circuit from the Southeast. This is from someplace out here west, where you have kind of the linear lines, north, south, east, west, straight roads and that sort of stuff. But still, it gives you an idea. Basically, those kind of green dots are switches for reconfiguration of the actual distribution system. And those tie switches are really those blue dots, right? And of course, distribution circuits don't necessarily run just straight down the road. They kind of do this web type fashion like you see here. But the idea is that even here, if you imagine that all these switches are automated, meaning that they can automatically open and close, based on local conditions and an algorithm. The idea here is still to decrease outage time, balance substation load, manage voltage profiles, that sort of stuff. So effectively, with more and more equipment in the system, you start to be able to stack those values. But things do get really complicated really quickly, because you can see that, well, you actually have 6 different feeders or tie points. They may not all connect to individual feeders. They may connect to a single feeder multiple times. But you have to figure out how the whole system actually works. But just an example of how this really looks in the real world. So even those simple examples sometimes can be quite complicated. It get very complicated very quickly. I think we're ready for a poll here to talk about specifically. Carrie, if you could bring the poll up, I think. Perfect. Yeah. So just real quickly. Would like to get some feedback from everyone on the call listening here. So in your states or regions or areas that your purview is relevant to, what is perceived as the primary driver for distribution automation? Are people doing this to reduce utility operation costs, right? Fewer truck rolls and customer calls, that sort of thing. Improved reliability, meaning reduced outage time or improved SAIDI and SAIFI. Improved distribution performance, meaning more efficient operation or better voltage regulation, or there really isn't a push for distribution automation in your area. If you could please vote and give us some feedback, that'd be great.
We're going to give you just another moment. See if we can get a couple more votes in. All right, we're at just about 50%, so we're going to close the poll.
Perfect. Thank you, Carrie. Yeah, I know it's lunchtime, so a good number of people are eating that sort of stuff. Oh, it looks like we missed the. Can you bring up the answer, Carrie?
Yeah.
Or the.
Press share.
There we go. Perfect. Oh wow. Okay, so this is very definitive. People are looking at improved reliability. That's fantastic. That's really good feedback. Okay. Well, we'll try to. Well, actually, I think the next couple slides are going to get into that quite a bit, and we'll try to focus on some of that. Perfect. Okay, so next slide, please. Let's go to slide 6. So let's talk about some distribution automation examples before we get into kind of the much larger, complex distribution automation conversation with advanced distribution management systems. This is an example here of using implementing conservation voltage reduction using the let me just describe conservation voltage reduction to begin with. So this is an application that you're probably familiar with, but the idea is that from a voltage regulation standpoint, effectively the users can have a lower bill, use less energy if they're actually provided a voltage that is not at the high range of the ANSI C84.1 range. So basically, still within appropriate range, but at a lower voltage. But of course, on long distribution circuits, it's kind of hard to actually regulate the voltage. Lots of times, all things being equal, you would like to have a really high voltage at the beginning, and then kind of at the very end of the line, you would have the lowest voltage. That would be the most sort of efficient use from a distribution design standpoint. But as we have more and more, when I say efficient, I mean using the full range of voltage, not necessarily actually energy efficient. Conservation voltage reduction is all about trying to flatten that voltage curve out so that more customers get a voltage that is actually, fairly low and thus energy conserving within their home and for all their loads. And that's really what can be shown here, is that at all these different levels here, coming out of the substation, that's that SS, you go through usually what's called a load tap changer. Not all utilities have those, but basically it can set the voltage, regulate the voltage to a specific range coming out of the substation. And then as you go down the line, say the circuit might be 7 miles long or even longer sometimes, there might be a voltage regulator, that's that reg box, and then there might be a capacitor bank also for voltage regulation and also reactive power compensation. Anyway, you get a voltage regulation curve that looks sort of like one of the figures there in the bottom. So the gray one, for instance, would be what kind of happens if you don't have any equipment out on the line, right? If you don't have a voltage regulator, you don't have a capacitor, you might get something like that. If you do have a regulator and a capacitor, voltage regulator and capacitor out on the line, you might get something that looks like the solid kind of green line. And you can see that this is centered around 120 volts, kind of the standard service voltage that we're expecting. Some people are a little higher, some people are a little lower, right? That's kind of normal. But if you start trying to do conservation voltage reduction, what you're trying to do is get that dotted line, where you're actually controlling your equipment to actually get that voltage as low as you can, again, within the proper range. So, nothing lower than 114 volts on 120 volt base. That's the basic idea behind conservation voltage reduction. How does that what does that mean in terms of distribution automation? Let's go to the next slide. When you have a bunch of actual equipment out on the line, again, voltage regulators, cap banks, maybe even PV inverters, distributed energy resources that may be able to play into this, may be able to actually be controlled, right, via utility control, and you have a complex distribution management system on top of this that's seeing all that information coming back and providing set points, right, you might actually be able to do a really good job of conservation voltage reduction. Or that's one of the ideas. So it's really the game for conservation voltage reduction is taking all the controllable elements that you have out on your circuit, all the data that you can actually see, and then actually come up with a solution in order to regulate that voltage as best as possible. Let's go to the next slide. Some examples of where this has actually been done, for instance, at AEP, they did a very interesting study looking at really what the value was, right, of actually implementing CVR via these different methods with different levels of distribution automation. What they did in their case was really apply data from end-of-line sensors, right? So these were extra sensors added to the system in order to actually see what the voltage was, say, very far out on the circuit, at the end of the circuit. So it's adding extra visibility to the system and seeing whether they could actually get enough benefit out of those systems in order to, A, pay for those end-of-line sensors, but also obviously benefit their customers and that sort of stuff. Using those end-of-line sensors, they really coordinated capacitor operations in order to keep the power factor at the substation near unity. That's trying to manage substation efficiency, so that's good as well. And what you can see here, right, is that from a customer energy reduction standpoint, again, this is a completely automatic system. It's active. It's reading those end-of-line sensors. It's making a decision. It's changing what the load tap changer and the voltage regulator and capacitor settings are, not on a second-by-second basis, but on a relatively fast basis, probably something like 15 minutes. They can get results that are about 3% improvement in, customer energy reduction. That's obviously saving, potentially a ton of money across the entire circuit, but also peak demand reduction, right? So that's a value that goes specifically to the utility, right? During those peak days they can actually see a benefit from this as well. Trying to defer the construction of peaking plants, right? So there actually could be a lot of savings and that sort of stuff in that sort of distribution automation example. Let's go to the next slide, please. Here's another case where I think this is a really good example of the stacked value of distribution automation efforts, right? So again, this is from Virginia Power, Dominion Power, their Virginia operations, really using advanced metering infrastructure. Emma actually talked about this, how those advanced meters can measure voltage, and oftentimes they don't actually report that voltage back. But in this case, that's exactly what they did, is they built up a use case for, well, if we get basically the AMI voltage data back, right? We got to actually do the data backhaul and all that stuff. But if we get that back, we can use those ALIS sensors for what the voltage actually is at our customers' locations, and then actually do CVR in a very fine way, right? Conservation voltage reduction, making sure everybody has the right voltage, but getting as close to the low voltage limit as possible. So they really went through this value determination, looking at multiple streams to enable conservation voltage reduction, because again, you have to pay for the meter. So if you look at that chart, the blue colors are costs. So you have to install the meter, right? You have to do business integration, get your IT people on board, get the IT set up, that sort of stuff, and distribution upgrades. So you kind of start basically $500 in the hole, right? Because that's what it costs, right? But immediately you see that big green bar, right? That's that energy conservation term. So for that value, right? I shouldn't say $500. This is looking at their total service territory. So these are millions, excuse me. But that energy conservation number, is huge, right? And it's that green bar, and it gets you into the positive territory. You look at storm restoration. So Emma mentioned that smart meters can send out a ping that basically says when they don't have power, right? So that helps with storm restoration. There's also obviously a benefit from customer service and metering, right? So again, you have higher quality metering. You don't have to read those meters every month. Automatic meter reading, that sort of stuff. So you end up with the total net value of about $800 million in this case from that study. But I think this is a really good example of how adding elements to the distribution system and stacking them up can get you a value, get you the true value, right? And this is really how these sorts of things are paid for. Obviously, energy conservation is the biggest one in this study, but again, it's a good example of that stacking distribution automation value. Let's go to the next slide, please. Okay, let's talk about advanced distribution management systems. So I mentioned that these can be very, this is really the complex version of distribution automation. So I really like to call this the whole enchilada, right? So if you look at applying control to your distribution system in a very big way, you tend to end up in what's called, advanced distribution management system, or ADMS. There's a lot of different definitions, I would say, for ADMS out there, but let me go through a couple points that I think are important to hit on. One is that you're really looking for the seamless integration of a system of systems, right? There's a lot of different systems at the utility, and the ADMS is really trying to integrate those all together in order to get the most value, right? So you're taking data from some applications that maybe that's not for instance, you take data from billing. Obviously, the main driver for that is to collect money and get people's bills right. But there may be data that's coming from billing that actually can help you from an operational side as well, and vice versa for that matter, right? So that's a good example of kind of data integration. The idea is that you're usually trying to share a common platform, right? So that's the overall platform that the ADMS is trying to integrate together. And then data used for management is used for other analytics, right? Like I mentioned, billing can be leveraged, that sort of stuff. And application-wise, usually what an ADMS really is kind of like an application framework. So you can think of your iPhone, right? You have iOS on there or whatever, and you can put whatever app on there you want. Some utilities are going to want a lot of apps. Some are going to want a few apps. And that's really what's shown here on the right. If you kind of look at the ADMS is kind of that square in the middle, and you could have SCADA integration. You could have volt-var optimization in there. You could have smaller control systems called distributed energy resource management systems, et cetera, right? You could even get your planning involved there. But the real idea is that all the data is coming in. That's, say, the bottom piece there. You might have AMI data coming in. You have weather data coming in, all your GIS, all that sort of stuff coming up into the system. So it's a data integration. You then have apps that can address all that data if they want. And then you actually have coming out the top feeder automation. Please click forward 1 or 3 times, I think, because that's what we'll highlight here real quick, right? That you just have the data integration. There we go. Yep, so it connects multiple data sources. Click again, please. You have multiple apps, and then finally, click one more time. It connects to real hardware, right? So at the end of the day, this is where distribution automation really gets into it, right? You have feeder automation, another word for distribution automation. You actually go out to elements of the distribution system which are controllable in order to get done whatever you're trying to get done. Let's go to the next slide, please. Oh, actually, I think here we were going to have another poll, if I'm not mistaken. I wanted to ask what the primary concerns that you've heard about or thinking about regarding advanced distribution management systems, ADMS, right? Are you most concerned about, say, cost of implementation, cybersecurity, integration with field assets, the communications infrastructure required, or you're not really looking at ADMS in your area.
Great, we'll give people a moment to answer. We're about 30% voted. Thank you all for participating. We'll give it just another moment. Let everyone's computers load.
Okay.
All right. We are significantly over 50% now, so we'll close the poll and show the results.
Perfect. Okay, wow. So definitely cost seems to be number one. There's no doubt that ADMS systems are costly, so I completely agree with that one. And integration with field assets, basically interoperability and actually getting everything to actually work. I think those are, well, this obviously pretty shows concerns across the board, which I think is very reasonable. But I agree, cost is always a big concern. Okay, that's very insightful. Thank you. Let's go to the next slide, please. One thing I did want to mention, so actually this is a good lead-in. There's a lot of questions with ADMS, and one thing I want to just quickly mention is that NREL has what we call an ADMS testbed. This has been supported by largely by the Office of Electricity, which very much thank everybody for their support on developing this. But what it really is it's a system actually within our lab where we can look at those sorts of challenges. We can't really look at cost. Cost is more an issue with you know, the talking to the vendors and that sort of stuff. But what we can really look for is really the benefit side, right? So if you're looking at cost-benefit analysis, we try to look at the benefit, where utilities simply don't know, you know, hey, if I implement this application, it's going to cost me X, but is it really going to work? Is it really going to give me a certain value, or does it actually work with this sort of utility equipment? That's really what the ADMS testbed is really meant to look at, is those benefits, so we can actually take distribution circuits and model them from any utility and implement an actual ADMS system, again, kind of whatever vendor they might be looking at, and actually see how it really operates on a handful of circuits so that they can actually figure out how this would look across their entire service territory. Also, if there's pieces of equipment via grid modernization efforts that utilities are looking at interconnecting with or interoperating with, we can actually test those interoperations as well in the lab. So we have the real physical piece of equipment, and as far as the ADMS knows, it's set up as if it was you know, a new PV inverter, for instance, that now is going to be controlled under controlled by the distribution system operator. As far as the ADMS knows, it looks like it's actually operating in the field, even though it's actually in our lab using power, hardware, and loop experimentation. We also have some advanced visualization capabilities in order to actually, because there's a huge amount of data that comes out of this, to actually figure out, you know, hey, what's actually happening? Is the ADMS providing better voltage regulation, for instance? Is it providing higher efficiency operation? Anyway, just a quick plug for the ADMS testbed. Let's go to the next slide, please. Okay, so I just wanted to talk real quickly about a path towards resilience, right? So obviously the more equipment that you have in the field and the more ability you have to control it, you have better visibility, but you also have better control. So it means that you can actually respond to things you may not be anticipating, like you know, weather events, that sort of stuff. Please click forward 2 times to get the screen showing the pictures. So the picture there is actually from Vicksburg, which you know, just west of Jackson there. But you know, obviously you have your fair share of extreme weather and that sort of stuff. The idea is that when you have these sorts of events, right? I mentioned the auto recloser scheme. That all works well, you know, for specific situations and that sort of stuff, right? But when things get a little bit crazier, right? Say you have multiple sections that are faulted, right? Or there's a lot of different situations where even those sorts of systems may not operate the way you think. And again, I put this figure in here. The idea is that if we have a lot of equipment out in the field, we have a lot of automation, we have a lot of options to actually try to be resilient, right? Feed lots of different customers from different directions, different paths for different flows, all that sort of stuff. When we do that, like from a reconfiguration standpoint, it all looks simple enough. But the other thing the utility, of course, has to look at is, can we regulate voltage in this new scheme? It's completely a circuit configuration that maybe no one ever thought of, you know. And when you have, again, say maybe a lot of visibility of what the voltage actually is at different customers, you have the ability to actually implement that, you know, very quickly and and get things up and running. So basically, there's just much more, there are many more options and greater flexibility in the system, which is one of the big pushes in the resilience space for distribution automation and control. Let's go to the next slide. Along with that comes really these cybersecurity considerations, right? So, you know, when you have an ADMS, you have a lot of communications going on, and that was reflected in the poll we just talked about, right? You have data coming in, obviously, from AMI systems and all that sort of stuff, SCADA and whatever. But you have a lot of data going out, going to these controllable devices, either utility devices or maybe customer-owned devices like PV inverters or EV chargers or whatever it might be. And I don't want to belabor what, because Emma did a great job kind of scoping this space, but I just want to mention that, you know, there are cybersecurity implementations because you have to protect effectively the data coming in and the data going out, right? Using obviously best practices. And you're effectively potentially, if you don't do this right, you have the ability to be more resilient, but you also have a larger, say, attack surface is what a lot of the cyber people would say, because you just have more connections and more smart equipment out on the system. Luckily, the physical underlying realities, meaning that the power system does operate under the physical, you know, the power flow on a system is based on the physics of the system. Lots of times we can use that effectively as a check to make sure that the data we're getting actually makes sense. So if the data doesn't make sense, it means that the power flow is not operating that way. That's a physical connection. Luckily, in the real world, it means either the system's not connected that way or we're getting a bunch of bad data, maybe from a nefarious, you know, malicious control or something like that. Let's go to the next slide, please. So I have just a few minutes here, but I want to go through an ADMS case study to give you kind of this an idea of how distribution automation control can add benefit for some specific cases that utilities are looking at quite often. Let's go to the next slide, please. So again, this was done using the NREL ADMS testbed, but there's lots of different ways to do it. The objective of this study was really to look at how varying levels of distribution automation equipment, excuse me, basically different levels of distribution equipment that could be controlled by the utility could allow extra benefit in terms of efficiency of operations, right? And this is specifically in a case looking at lots and lots of distributed energy resources, right? Or lots of variable renewable energy sources, like, for instance, PV. So in this case, we're looking at, you know, a large, 5 megawatt distributed PV system. This is very typical, say, of kind of North Carolina, type area. The way they're seeing PV being rolled out currently, connected to distribution. We see this a lot in California as well. Don't want to single out North Carolina, but the question is with that 5 megawatt PV system ramping up and down a lot, it does have a large impact on the voltage regulation equipment on the system as well as the customers. How do we try to mitigate that as best possible? Let's go to the next slide, please. So just to give you a very rough idea of the kind of the system that we're looking at, it is a medium voltage system, right? I would say this is all pretty typical. It has a number of voltage regulators and a number of capacitors on it. Effectively, these are the tools that the utility currently had, say, before the PV system was installed, in order to control the voltage on the distribution system, you know, do CVR or not, or whatever they're trying to do, right? But just want to give you an idea that this is, you know, pretty typical system. There's a very rough diagram there in the upper right, but suffice it to say, this is, you know, probably something that doesn't look too far off what you see down there in the southeast quite often. Let's go to the next slide, please. So the control modes for the PV inverters. So I mentioned that there's a large PV system on there. There's actually more than one, but the main case is this 5 megawatt large PV system. There's a lot of things that those PV inverters can do. Again, this is kind of from a control standpoint. They can do constant power factor set point control, meaning that you just say, hey, operate at 0.95 lagging all the time, right? That would be a good example of that. There's also volt-var curves, meaning that the reactive power output that the PV inverter would supply depends on the voltage, right? So these are all things meant to try to mitigate the impacts of that large PV system that it can do if requested to do so. And we'll see how that plays out here in just a minute. Let's go to the next slide, please. So I'm going to just show you, there's a number of scenarios. This gets a little complicated, but I'm going to try to show you really just some basic scenarios of how the system performed with no control, kind of the baseline. And then as we include more and more, say, distribution automation, right, or distribution control, you'll see that the operation of the circuit becomes better and better and better, right? So first we'll really look at the PV system doing local control. So we're not really considered distribution automation, but basically just advanced PV inverters, which we all have now, doing two different modes. Then eventually we'll get into what's called legacy IVVC. This is really just volt-var control, integrated volt-var control is what it's called. Using, say, an ADMS, right? And then eventually, if we actually include even more equipment, what legacy means is the ADMS is controlling only the distribution utility-owned equipment, right? So voltage regulators and capacitors, a lot like the CVR study that we saw earlier, right? And eventually, if you actually include, say, the PV inverters, the PV control in that integrated volt-var control scenario, that effectively gives the control system even more stuff to control, and you'll see a benefit there. On the right, what you're going to see is we're going to really look at these results for 2 different days. One is a very nice clear day, kind of that orange line, and one is, you know, a cloudy day, the choppy red line. Obviously, the clear day is easier for the control system to control properly and that sort of stuff. So the cloudy day is more realistic of one of those challenging days that really we're trying to get our money out of an ADMS. In terms of reduced impact on the overall distribution system. Let's go to the next slide, please. So some of these are a little complicated. I do not expect you to be able to read all of these. What I want to point out here, right, is that obviously on the left is the nice smooth day, you know, clear, nice sunny day, and on the right is the cloudy day. I want to draw special attention to the lower graphs. What these are is the number of tap changes and the number of capacitor changes that the system sees during a day-long period. And what you're going to see here, and we'll go to the next slide in just a second, is as we increase the amount of control that is actually being implemented, the amount of things on the distribution system that the ADMS can really control, you're going to start seeing red shaded areas. And that is effectively showing you the difference in these graphs, meaning that what you want is the largest shaded area, right? So these baseline results are not good. These distribution the voltage regulators and the capacitors are switching on and off a lot, especially during the cloudy day, which is wearing those out. It's causing a lot of customer voltage fluctuation and that sort of stuff. These are the undesirable impacts of DER integration on this circuit. Let's go to the next slide. So this is the base case. Suffice it to say that the system is not behaving the way we would love, right? So if we go to autonomous local control, meaning this is the PV inverter, again, not really any major control, but it's just doing, say, a constant power factor operation, we actually get some benefit, right? So you now see some kind of red, or maybe it's pink on your screen, reduction in the number of capacitor bank operations and tap voltage regulator tap settings, especially during the nice sunny day, right? Still on the cloudy day, it doesn't help much, right? Things are just moving around way too much, and we don't actually have much benefit at all, even from that local autonomous control. Let's go to the next slide, please. So if we do local volt-var control, so the last one was constant power factor, we get a little bit better, right? So this is, again, local control, but doing volt-var operation instead of a constant power factor operation. You know, not a lot of difference, but at least on the local, on the highly variable day, we get a little bit of benefit. Let's go to the next slide, please. So now we actually start looking at ADMS implementation. So in this case, it's legacy, meaning that the ADMS is controlling the legacy equipment. And what you can see immediately is that there's these huge amounts of red, right? Which is really good. It means that we're dramatically reducing the number of capacitor bank operations. We're really reducing that wear out factor while still regulating the voltage and all that sort of stuff at the customer as required and that sort of stuff. So even with kind of basic ADMS operation, you can see a huge difference and effectively a massive reduction in the overall kind of impact of the circuit, even on the really variable day, right? So this is a really good sign. If we go to the next slide, we will see even more red in some ways. So this is really integrating those advanced inverters into the overall computation, or basically what it means is that the advanced inverters can be controlled by the ADMS, and they can respond to set points. And we see an even somewhat increased ability. So basically what's happening here is the ADMS is doing really fast changing variable, say, voltage regulation with the PV inverter capability, because it's good at doing really things very quickly. Whereas longer term, slower regulation is really being done by the voltage regulation equipment. For lack, I mean, that's what's happening. Okay. Anyway, I just want to give you that brief idea that basically, again, the more stuff that is controlled, really, the better. But these are the value propositions that utilities are really looking at trying to make. Do I just regulate my own equipment? Can I get done what I want to get done? Is it worth trying to go and actually control customer equipment, right? Or do I just not have an ADMS at all and use a constant power factor or a volt var regulation for DERs? These are all good questions, and that's exactly what this system is really meant to try to answer, and some good examples of what this would look like in terms of, well, an actual case study that was done for specifically this reason. Okay, let's go to the next slide. I think I'll skip this one in the interest of time. I want to leave some questions, time for questions, so let's skip this one. And then, yeah, the case study conclusion, I think, is probably pretty obvious, right? That there were obviously substantial improvements when the ADMS was applied, and even more so when the ADMS had more and more to control, right? Anyway, I'll leave this for people to read if interested in the future. I think that's the end of the presentation here that I had. Thank you all for your patience and willingness to get on a call, and for polling as well. I really appreciate the feedback that was given during the presentation.
Thanks, Barry. This is Lisa. I've got a couple questions here for you. What's the rough percentage of utilities that have AMS, that have
ADMS? Yep.
That use conservation voltage reduction or volt var optimization, and I'm also interested in ADMS.
Okay.
Those two.
Yeah, these are all good questions. So CVR, I'll start there. It's actually pretty variable, right? So for instance, one of the coolest things about probably all the jobs of the people who are giving these presentations, we get to work with lots of different utilities. So the regulators oftentimes set the set the expectations for conservation voltage reduction. Some states, for instance, basically require the utilities to have a conservation voltage reduction capability or plan. They don't all have to do it the same way, right? California is that way, where the 3 large IOUs all do CVR in a different way, but they all have to do CVR in some way. Other utilities, they don't even know what it means, right? Like, what are you talking about? So I'm going to guess that for large IOUs, the percentage is quite high. For smaller municipals and that sort of stuff, I think CVR is probably pretty low on their list of things that they're looking to do. I will say that CVR is also a difficult. Yeah, sorry, go ahead, Kevin.
Oh, one thing I was going to add is that this is also a technology that's not uniformly deployed across utilities. So while you may have a large utility that has deployed CVR, they probably have not deployed it on every single circuit. So I think if you look at the total number of circuits in the US, well under 1% probably have CVR actively employed on them.
Yeah, good point. Because there are circuits where CVR just doesn't make sense. By lowering the voltage, you won't actually get an efficiency boost, right? So lots of times, if somebody does implement a CVR program, they go after the circuits that will have the largest efficiency increase to begin with, which just makes sense. In terms of ADMS implementation, this is again pretty variable. I would say the large IOUs definitely have ADMS, but everybody's looking at it. It's pretty wide scale and growing quickly. Definitely the list is growing quickly. I would say 5 years ago, the list was actually quite short. I don't know, 5, 6, 7 maybe that were really using it in a big way. I think that list has probably grown dramatically in the last 5 years. Again, this hasn't probably gotten down into a lot of the munis and co-ops as quickly. But again, the scale for ADMS is pretty variable, right? You can have a pretty simple ADMS that's just doing a couple applications versus one that's doing 20 applications. So I think we're going to see people adopt a couple applications that make a lot of sense, and then maybe it'll grow from there, or maybe it'll stay there if that's where it makes sense.
And great. And just one more question before we take a lunch break. And if you can answer briefly, I'm looking for some examples of specific types of end-use equipment for both residential and commercial that may see reduced electricity consumption as a result of conservation voltage reduction or volt-var optimization.
Yep. So I think this person is probably getting specifically at a lot of the classic example for CVR were things that worked really well with CVR were incandescent light bulbs. We don't have a lot of incandescent light bulbs anymore. And this is why CVR in some ways is losing some of its efficacy, although there are studies that actually kind of counter that as well. So it's difficult to say. There are a lot of elements that I would say are not really reactive to CVR anymore, right? So pretty much all your power electronics in your house, that sort of stuff. It's probably actually more efficient at a high voltage, ironically. Not by much, but by a little bit, right? Until the voltage gets obviously too high, which you don't want. There are still some efficiencies to be gained probably in motor-driven equipment. Depends on how old your, say, refrigerator is. New refrigerators actually have a power electronic motor speed drive in them sometimes, if it's kind of a fancier refrigerator or something like that will. In which case they won't respond to CVR at all. But older direct drive, simple motor compressor systems, that sort of stuff without a speed drive, there's been some evidence that they do still, they are more efficient at a lower voltage, that sort of stuff. I know PNNL has done a lot of work on this in the past. Kevin, did you have anything to add?
Yeah, there isn't, I wouldn't say there hasn't been a comprehensive study of here's all the end use appliances and their performance by each. We did a few of those probably a decade ago. I know EPRI's done some, but generally what you see are utilities that have done this type of study, and they'll apply it to general classes of loads, such as residential electric heating versus residential gas heating. And there are a number of different papers out there in the literature with that type of material available.
Thanks, Kevin and Barry. And just one more question from one of our listeners. How can utilities future-proof automation equipment prior to deployment of automated distribution management systems? This is about future-proofing.
Well, that's a big question. I think just thinking about future-proofing is probably step one, right? I think looking at the interoperability of these systems, right? Like how are these really going to be implemented? One thing I will say is I think the comms infrastructure is one of the challenges, right? If you have equipment out in the field and you think you're going to be talking to it for the next 30 years, right? Because that's going to be there for 30 years. The question is what comms infrastructure you're going to use. You don't want the control and the comms to be tied together. Otherwise, you may have to change it as often as you change your comms, right? So I think those sorts of interoperability between comms and control and actual physical devices themselves is probably the trickiest point. There's a ton of work going on in that space. Things like the ADMS testbed are really good for proving some of these out, right, in terms of actual flexibility. Can I use these 7 different comms types, right? Because you don't know exactly which one you're going to end up with 5 years, 10 years down the road.
Barry, 2 things I'd like to add to that is, one is road mapping out what you want to do, because a lot of these different systems, they don't exist in a vacuum. They rely on other systems. So asking yourself, in the next 10 to 20 years, what else will we deploy and how might that interact with what we're deploying now? I think communications is the great example of, if you build out your communication system for only one function, then when you roll out the next one, you may need a whole new communication system. So you need to evaluate how much should we overbuild stuff for what we expect to be coming down the road in our plan, not just as a general, just in case. And then the second is looking at what Barry was getting at, was the interoperability of, as we start to deploy these systems, let's say we deploy a DMS or an ADMS today, if we know that we're going to plan on deploying an AMI system, automatic meter infrastructure, have we bought an ADMS that can integrate that, or how might that look like? Just so that you're thinking ahead and planning your building blocks instead of every time you come to a new point, you have to reevaluate from scratch.
Great, thank you so much, Kevin.
Yep, perfect.
Barry, back to you. Carrie.